Hi everyone and welcome to session 13 of Field 2002, Logic, How to Defeat Your Foes with Reasoning. Let's have a brief recap of what we've done so far in the course. In the first module of the course, we had a look at propositional logic. Propositional logic is very basic language that allows us to translate arguments from English into a formal system and then prove things about them. We introduced the key notions of validity and invalidity, soundness and unsoundness. We had a look at the syntax for propositional logic, we introduced the semantics for the logic, and then we introduced two proof systems, the truth table proof system and the truth tree proof system, which allowed us to prove whether or not an argument is valid or invalid inside the language. From there, we started on module 2 of the course, and in module 2 we're looking at our next language, which is monadic predicate logic. In the first couple of sessions, I introduced you to the syntax of monadic predicate logic, and the syntax of monadic predicate logic combines our basic propositional connectives, things like not, or, and, the biconditional and the conditional, with universal and existential quantifiers, which allow us to talk about everything or something, and also predicates, which allow us to talk about the properties that objects have, and then names, which allow us to name particular objects, and variables, which when used in combination with the quantifiers and predicates, allow us to talk about groups or classes of things and specify relationships between those groups without having to name anything in the groups in question. From the syntax, we then moved into the semantics. And the semantics for monadic predicate logic is this thing called model theory. And what we have for each of our, each group of sentences that we're given in monadic predicate logic, we have a semantic interpretation which we call a model. Now a model has three things. It has a specification of a domain of objects. It has a specification of the extensions of any predicates that appear in the sentences that we're attempting to model. And then it has the assignment of an object to each name that appears in the group of sentences that we're trying to model. When there are no names appearing inside our group of sentences, then we don't have to assign them to objects, but when there are names appearing in the group, then we have to assign them to something inside the domain. So you can't have empty names, names that name nothing. You also can't have an empty domain, a domain of no objects. There always has to be something inside your model for monadic predicate logic. The syntax plus the semantics gives us a working language, and it gives us the ability to translate out arguments into monadic predicate logic. So we can take this argument, all people are animals, Sally is a person, therefore Sally is an animal, and we now have the capacity to translate it out as something like this. For all x, if x is a person, then x is an animal. A, which names Sally, is a person, therefore A, which names Sally, is an animal. So we've got a sense of how to translate out arguments, and we've also got a sense of what validity looks like inside monadic predicate logic. Inside propositional logic, validity is just defined in terms of possibility and impossibility. Inside monadic predicate logic, we define validity over models. So inside this language, an argument is valid when there's no model in which the premises are true and the conclusion is false, and an argument is invalid when there's some model in which the premises are true and the conclusion false. Because the models each correspond to parts of possibilities, when there's no model under which the premises are true and the conclusion false, it follows that there's no possibility under which the premises are true and the conclusion false. And when there's some model under which the premises are true and the conclusion false, it follows that there's some possibility under which the premises are true and the conclusion false. So you have this tight connection between the model theoretic semantics that we're using to interpret the language, the concept of validity as defined over those models, and then the concept of validity that we had in propositional logic. What actually happens is that validity inside monadic predicate logic really implies that basic notion of validity that we started with, involving possibility and impossibility. So we've got a sense of how to translate out arguments, we've got this more complex language, we've got a sense of what a valid argument is going to look like in this language. What we don't have yet is a method for determining validity or invalidity inside monadic predicate logic. And so the last thing that we're going to do in order to finish off our understanding of this language is develop a proof system that enables us to prove whether or not an argument is valid or invalid, based on the new syntactic and semantic structures that we're interested in. So we're going to do two things. The first thing we're going to do is introduce a proof system. What we're going to do that is take our truth tree system that we had in propositional logic and add some extra rules in order to handle the new items that we have inside this language, things like quantifiers and predicates. And we're also then going to modify the background sort of meta rules that govern the proof system itself, the completion and closure rules, so that we have an understanding of how to finish trees inside this language. The second thing we're going to do is we're going to look at what a counterexample looks like in monadic predicate logic, and we're going to develop a strategy for reading off counterexamples from the logic. And when reading off counterexamples from the logic, I'm going to show you how to build models that correspond to those counterexamples. And then we're going to have a look at what are called infinite trees. So one of the difficult things about monadic predicate logic, and indeed the next language that we'll look at as well, general predicate logic, is that the truth tree system can actually produce an infinite structure, which means that you can sit there doing the truth tree and it will go on forever. We'll have a look at what some infinite trees look like later on. We'll consider what the implications of infinite trees are, both with respect to determining validity and more generally what it means for the language that you're interested in. And we'll look at ways to solve those infinite trees. All right, so let's get started. Let's take a step back and recall what we're looking for. We're looking for a foolproof method with which to determine whether or not an argument is valid or not. The truth table system won't work in monadic predicate logic because the semantics that we're using, the semantics that I introduced last time involving models and extensions and so on, is not as completely specified by the truth tables as it is in propositional logic. So we have to move away from the truth table system, and that's why we introduce the truth tree system in propositional logic, so that we can then carry that system over to monadic predicate logic and then use it for the rest of the course as well. So we're going to take the truth tree system, we're going to dial up the complexity of it a little bit. So just to remind you of how the truth tree system works, what you do is you start with a group of sentences at the top of your tree. And what that means when you start with that group of sentences at the top of the tree is that you're saying all of these sentences are true together. And then you unpack those sentences in order to get down to their basic constituents, down to propositions and the negations of those propositions. When you have a proposition and its negation appearing on the same branch, you close that branch, and when you don't, then you leave the branch open and you continue to complete the tree. What we had was a sequence of rules for each of the propositional connectives that we had in the language. We had the disjunctive rule for disjunctions, and when you strike a disjunction, what you do is you tick it off and you branch it into one side having the one disjunct and then the other side having the other disjunct. With the biconditional rule, that's also a branching rule. On one side, when you've got alpha biconditional beta, on one side you've got not alpha and not beta, on the other side you've got alpha and beta, and that's just representing the way in which things that are connected by the biconditional stand or fall together. For the conditional, you've got on the one side, when you've got alpha, arrow, beta, on the one side you've got not alpha, on the other side you've got beta, and that represents the two situations that cover all of the true cases for the conditional, namely when the thing on the left-hand side is false or the thing on the right-hand side is true. Then we've got the conjunction rule. What the conjunction rule tells you is that when you've got a conjunction, you tick it off and you just conclude that both conjuncts are true. So you just have a column under which you write each of the conjuncts. The double negation rule, double negations cancel. And the double negation rule can be used for multiple negations in a row. So let me just quickly show you what that looks like. So suppose you've got something like this. So we've got a sequence of negations. We've got not A. What we do in order to manage this when we're handling it inside the truth tree system is we cancel our double negations in pairs. So the first thing we do is we're going to strip off these two double negations right out the front because they cancel, and we get to not A. Then we cancel these next two to get to not A. And then we cancel these final two to get to A. And it doesn't matter how many negations you've got, you always just cancel them in pairs until you get down to a point where you can't cancel them any further. So for instance, if we had an extra negation along this sequence, then we would cancel until we got down to not A. The important point to note is that the double negation rule applies no matter how many negations there are, so long as you've got two or more. Okay. So we've got this truth tree system for all of those basic propositional connectives, and then we've got a rule for each of the negated connectives. So we've got the negated disjunction rule, which is a column rule that tells you that when it's not the case that alpha or beta, then not alpha is true and not beta is true. When you negate the biconditional, it branches. On one side, you've got alpha falling and beta standing. On the other side, you've got alpha standing and beta falling. When you negate the conditional, you've got alpha and not beta being true together. What you are basically identifying is the case that makes the conditional false when you've got the first thing and you don't have the second thing. The negated conjunction, That's a branching rule. It branches to either the conjunct on the left is false or the conjunct on the right is false. So either alpha is false or beta is false. And then we've got the closure rule. The first closure rule was that when you've got a proposition and its negation on a branch, that branch closes. And then the completion rule tells us that a propositional logic tree is completed when either every branch closes or every rule that can have, or every proposition that can have a rule applied to it has had that rule applied to it and been ticked off, right? So we've got that global structure in order to tell us how to close and complete trees. All right, in order to extend the propositional logic truth tree system over to monadic predicate logic, there's some good news and some bad news. The good news is that all of the propositional connectives and all of the rules for those connectives in the propositional logic, those get carried over. So the rule for the disjunction stays the same, the rule for the conjunction stays the same, the rule for the conditional, biconditional, negated conjunction, negated disjunction, negated conditional, negated biconditional, double negation, all of those rules are exactly the same inside monadic predicate logic. So that's the good news. You don't have to learn a whole sequence of new rules to handle all of those. The bad news is that we do have to add some more new rules in to handle the quantifiers inside the language, and we also have to modify the global structure of the system. So we have to modify the completion and closure rules so that we can actually understand when a tree is finished inside monadic predicate logic. So what we're going to do is we're going to go through this in two steps. We're going to look at the new rules for the quantifiers and the negated quantifiers. So we're going to handle those two types of cases first. And then we're going to look at those global rules, and then we'll look at some specific examples. I'll do some trees for you so you see how this all works in practice. Okay, we're going to start with the negated quantifier rule. So these are cases where you get anything like this inside a tree, where you get something like not for all x, px, right? So you've got the negation right out the front of a quantifier like that, or the universal in this case, or you could have it for the existential as well. We want to know how to deal with those sorts of cases when you've got a negation and a quantifier. The negated quantifier rules are the easiest rules to handle. The unnegated rules are the hard ones, and indeed it's the universal quantifier and the rule for it that's going to bring about all kinds of trouble. In particular, it's this thing that can generate the infinite trees that I mentioned previously. So we've got to keep a careful eye on how that universal quantifier works, because it can lead us into strife if we're not sufficiently precise about how it's being used. Okay, so let's start with the negated quantifier rules. So the first negated quantifier rule is the negated existential. So that's anything that looks like this. Doesn't matter what follows the existential. I'm just going to put some random propositions. So here we've got a negated existential. And what we want to know is, well, when we see that sort of thing inside a tree, what do we do to it? The answer to this is fairly straightforward, and it actually comes from something that I mentioned about the quantifiers quite early on when I was introducing them syntactically. One of the things that I mentioned about the quantifiers is that the quantifiers are duals of each other. And what that means is that you can convert one quantifier into the other via the negation. So for instance, you can take an existential quantifier and turn it into a universal quantifier by modifying that existential quantifier with a negation. Similarly, you can turn a universal into an existential by modifying that universal quantifier with a negation. So the rule for the existential is fairly simple. What you do is you reverse the quantifier. So if it's an existential, you turn it into a universal quantifier, and then you move the negation to just in front of the quantifier, and then you write the rest of the proposition. So basically what we're doing with the tree rule here is we're really encoding that duality between the quantifiers. When you negate the existential quantifier, it turns into the universal quantifier with the negation moved over. And if we think of this in English, it seems fairly intuitive. If I say there doesn't exist something that has certain properties, then everything fails to have those properties, right? And that's what happens when we move the negation over. When you say there isn't something, we say for everything, it's not the case that. So this is the first rule that we have. And the first rule, which can be written in a general form, is like this, where alpha is any proposition in the language that's well-formed whatsoever. And what we do is we tick off the negated existential, we flip the quantifier and turn it into the universal and move that negation over in front of the existential between the quantifier and the alpha. And that's really important. You don't want to put the quantifier, you don't want to put the negation after the alpha, you don't want to put the negation between the quantifier and the variable. It always goes after the quantifier variable chunk and between the quantifier variable chunk and the alpha proposition that is following it. So that's why up here I moved that negation in between the universal and the AX and BX rather than putting it anywhere else. Okay, so that gives us our first rule. And that one's fairly straightforward. You just tick, when you have a negated existential quantifier, you tick the quantifier off and you swap it for the other quantifier with the negation moved over. The next rule that we're going to deal with is the negated universal. And the negated universal is exactly the same basic idea. And that's because the negated universal is also a dual of some existential proposition. So let's have a look at a negated universal proposition. So here we've got our proposition. It's not the case that for all x, if ax, then bx. And in order to handle this, what we do is we tick the proposition off, we turn the universal quantifier into an existential, and we move that negation into that space between the quantifier and the ax arrow bx. All right, so we've moved that quantifier into that slot there, and we've reversed the quantifier into the other quantifier sign. And again, this is quite intuitive. If it's not the case that everything has certain features, then there must be something that doesn't have those features. And that's what that means when we move that negation right in front of the quantifier like that. As with the negated existential rule, you have to move the negation into the right place, and that means that you move it after the quantifier variable chunk and before the proposition that the quantifier is actually quantifying over. So the rule for the negated universal, if we're writing it in general form, is like this. If it's not the case that for all x alpha, then we tick that off and we get there is something such that it's not alpha. And that negation goes between the variable and the quantifier chunk and the alpha, which is any proposition that is well formed within the language. So you can see that the negated existential and negated universal rules are very similar to each other. What you do in both cases, when you get a negated universal or a negated existential, is you turn the quantifier, whichever quantifier it is, into the other quantifier, and then you move the negation over in front of it. So really, you only have to remember one thing here, rather than having to remember two different rules. You just remember one broad strategy. When you get a negated quantifier, you flip it and you move the negation over. Okay, those are the easy rules to handle, the negated existential and the negated universal. The difficult rules to handle are the cases where we don't have any negation, so the unnegated existential quantifier and the unnegated universal quantifier. So let's have a look at those. So the unnegated existential quantifier looks like this. We've just got, there is something such that blah, whatever. So we can put in some sequence of propositions here in order to complete the statement. So what happens when we hit something like that in a tree? When we say there is something such that AX and BX, what do we do to that? How do we transform it using the tree rules? In order to work this out, we have to think a little bit about what the existential is saying, and then we modify the tree rule to kind of represent that information. So what does it mean to say something along these lines? Well, suppose that AX means that X is red, and BX means that X is round. What we're saying is there is at least one red and round thing, right? And when we put that into a tree, we're saying this is true. So we're saying it's true that there is at least one red and round thing. So given that's true, what can we conclude from the truth of that statement? Well, what we do is we say, all right, there is something that's red and round. Let's just give that thing a name for the purposes of argument. So let's say, let that red and round thing be A. And now what we do is we tick off the existential quantifier, we get rid of the variable, and we substitute it in for that name that we've given this object. So let's have a look at this in a little bit more detail. So here's our statement. And it can help to think of this in terms of the models that we've been building. So here's the universe, and we're assuming that this proposition is true of some particular universe. Let's just suppose it's our universe, and it says that there is something that's red and round. So let's just put that, actually, let's Let's actually make it red and round, shall we? So here's our red and round thing. And so given that we've seen this in the tree, that's what we know about the universe. There is some red and round thing. So what we do is we say, well, look, we don't really know what that thing is. We don't have a name for it. It could be Mars, could be anything. We don't really know. What we're going to do is, just for the purposes of argument, we're going to assign it a name from inside the monadic predicate logic. And then from there, we get rid of the quantifier. So we're drawing out the consequences of the quantifier, and the consequence of the quantifier is that there is something that satisfies the properties that are laid down by this quantifier, that satisfy this A and this B. So what we do is we tick this off, and then we put in the lowercase a here to keep us to sort of let us know that what we've done is we've let the thing that this existential is talking about be called A, and then we get rid of the variable and substitute it for that name. So the basic idea behind the existential quantifier is that in order to get rid of it, in order to deal with it when you hit a tree, you tick it off, you take a name, and you substitute the variable for that name in order to move to something like this. And once you've got this, you can then just do the conjunction rule to get down to something like that. And so what have we concluded? Well, given that there is something that has the properties A and B, what we do is we say, let that thing be called A. Now we can conclude that it's A, that thing that we've named A, that has the properties A and B. And from that, we can conclude that something has the property A, namely A, and that something has the property B, namely A as well. Okay, so that's the basic form of the existential, but we have to be very careful when we're using the existential. In particular, every time we reach an existential quantifier, we have to use a new name. Now, what does that mean? Well, it means that we can't use any name that's appeared above that quantifier in the tree up to that point. It has to be a new name to the branch upon which that quantifier appears. So let me show you what that looks like when we get it right, and I'll show you what it looks like when we get it wrong. All right, so have a look at this statement. So this will be a statement, this will be a case where we're actually going to get that constraint that I just specified wrong. So I'm going to use the existential quantifier now. I'm going to substitute in a name for the variable in order to get rid of the variable. But what I'm going to do is I'm going to use it in such a way that I haven't obeyed this broad constraint that it has to be a new name. So here's my tree so far. I've just got PA, QB, and then I've got an existentially quantified statement like this. All right, so I want to finish the tree, and in order to finish the tree, I've got to deal with this existential quantifier, although we'll talk in more detail about finishing monadic predicate logic trees in a moment. But let's suppose that I want to finish this existential. What I'm going to do is I'm going to tick this off and I'm going to put in some name. Now here's the wrong thing to do. The wrong thing to do is to use one of the names that appears above this existential quantifier in the tree so far. So if I use A and I substitute in AA and BA, then I've used the existential quantifier rule incorrectly because I used a name that was already above it in the tree. Similarly, if I put in B, which is also above that existential quantifier, and I get AB and BB out like that, then I've also used the existential quantifier incorrectly because I haven't used a name that doesn't appear in the branch upon which that existential quantifier finds itself. All right, so it has to be a new name, which means that you look above the existential quantifier up the tree, and you find the with respect to the branch that it's on, and then you look for a new name, one that hasn't been used so far, and you put that in for the variable. So now we can look at what the right thing to do here is. The right thing to do is to pick the first unused name. So what's the first unused name? Well, the first unused name in this case is going to be the lowercase c, and we're going to substitute in c for the variable, and we're going to get this A, C, and BC, like that, and then we tick this off, and we get down to AC, BC. All right, so that is correct. This is good. Make sure you use the first unused name to that branch. And that restriction is quite important as well. So it's the first unused name, but it's the first unused name on a branch. So what that means is, let me give you a slightly different example to show you the implications of it being the first unused name to the branch. All right, so have a look at this tree. Suppose that I do some tree and it branches like this, and then on one side I get PA, QB, and on the other side I get RC, PA, like that. And those are the only names that have appeared in the tree. But also on this side I have an existential statement. And over here I have another existential statement. Okay, so I've got two existential statements on two branches. Now I have to use some names in order to get rid of those existentials, and I'm going to have to deal with both of the branches. So let's start over this first branch. I look up the branch above this proposition, and I see that A has appeared on that branch, C has appeared on that branch, but B hasn't appeared on that branch. So the first unused name that I can use here is going to be B. And that's okay. As long as I don't use A or C, that's fine, even though B appears over on this branch. The restriction to using the first unused name only applies to the particular branch that the existential appears on. So over here, I look at this and I want to get rid of this quantifier, and I see that I've used A on this branch, I've used B on this branch, but I haven't used lowercase c, and so what I'm going to do is I'm going to substitute in the C and get AC, CC, then AC, CC, right? Now C appears on this left-hand branch, but it doesn't appear on this right-hand branch. So because it doesn't appear on this right-hand branch, it's okay for me to use it. And similarly, B appears on this right-hand branch, but it doesn't appear on this left-hand branch. And because it appears on the right-hand branch and not the left-hand branch, it's okay for me to use it on that branch. What I can't do is, with respect to either branch, use a name that already appears on that branch. So in this right-hand branch, I'm forbidden from using A or B to get rid of this existential quantifier. And on this left-hand branch, I'm forbidden from using A or C to get rid of that first existential quantifier. But I can use things that appear on other branches, so long as those things don't appear above the tree somewhere. So this is, I'm imagining this is sort of halfway through some tree. If I have either B or C appearing above this split, then that will count as being on both branches. So for instance, if above this split I actually find that I have a B somewhere, then that means I'm forbidden from using B on either branch down here when I get rid of either of these existentials. Similarly, if I have a C appearing somewhere up above the tree, then I'm forbidden from using the C on either branch. So what happens is that you can use any name that doesn't appear on a branch for an existential quantifier, but you have to look all the way up the branch to the top of the tree to make sure that that name isn't appearing somewhere above the branch that you're on, right? So you've got to look all the way up the top. You don't have to look sort of in a zigzag way. So if I'm trying to work out what names I can use, I don't go up and then down and then see that there's some name over here and then go, oh, I'm not allowed to use that name. You only look up the branch. You never sort of zigzag back down in order to work out what names you can and can't use. But you do have to look all the way up the branch in order to work this out. Okay, so that's the sort of core aspect of the existential rule. There are two important things about how the existential rule works. First thing is that if you want to get rid of the existential, and as we'll see later on, you do have to get rid of all your existentials, you're going to tick that existential off, you're going to substitute a name for the variable that follows the existential, and then you're going to get rid of the existential from the line that you write the variable substituted instance down on. The central constraint with using the existential rule is that you have to use the first unused name in that branch, not in the entire tree, just in the branch that the existential appears on. Now, one implication of using the first unused name is that if you have multiple existential propositions inside the same tree, or the same branch, sorry, then you're going to have to use new names for each of those existential propositions. So have a look at this statement, this tree. So suppose I've got PA, QB, and then I have EX, RX, right? So I've got one existential statement, and then I have a second existential statement. And now I've got to try and deal with these two existential statements in order to get through the tree. what I'm going to do is I'm going to start with this first existential statement, and I'm going to use the first unused name. And the first unused name in that branch of the tree is now C. So I'm going to use C to get rid of that existential. But when I hit this second existential, I look at that branch and I see that A, B, and C are taken, right? So before, when I said you go up and you don't look down, I meant that you sort of don't zigzag, you don't go up and down. But if you're looking to see which names that you can use with respect to a particular existential, you do look at the entire branch, both below you and above you, in order to work out whether or not you can use the name in question. So if I'm looking at this existential and I see that the name C has already been used by the time that I get to that existential, that means that I have to use a new name, in this case D, and then I get AD and BD, and then I can deal with that by ticking it off and just eliminating the conjunction. Okay, so that's really important. When you've got multiple existentials on the same branch, you have to use new names for each existential that you strike. And by a new name, I mean a name that hasn't appeared on the branch previously. So what you can't do is use the same name for these two things. So what I'm about to show you is wrong. So suppose instead of doing what I just did, I look at these propositions and I go, okay, well, I'm going to put A in for that one. Sorry, not A. I'm going to put C in for that one, and then I decide to put C in for that one as well, and I go, well, look, RC and AC and BC, and then I get down to this. All right? That is a mistake. I'm not allowed to do this. This is completely forbidden. And the reason that that's completely forbidden is that it makes an assumption with respect to the things we're talking about that we're just not entitled to make. What's the assumption? Well, look at what I'm saying in this tree. I'm saying there is something that has the property R, and then I'm saying there is something that has the property A and B together, right? At no point in the tree am I saying that these are the same something. We don't have the capacity to say that yet. Later on, when we get to general predicate logic, we'll have the ability to say that these are the same something. But right now, what we have to do is assume that every existential that appears in our tree is talking about a different thing, at least with respect to getting through the tree. A little bit different when we hit counter modeling, and I'll talk about that a little bit later. But with respect to breaking apart the rules inside the tree, every time we hit an existential, we have to assume that it's talking about a different thing. Because if we don't, then we might end up making a mistake. For instance, suppose that this first proposition says there is something that's red, and this second proposition says there is something that's green and round. If I put in C for both, then what I'm assuming is that there's something that is red and that that very thing is also green and round. But that's not an assumption that I'm entitled to make given the information that I have available to me in my tree. And indeed, if I assume that the thing that's red is also the thing that's green and round, you can see that that might lead me into a great deal of trouble eventually. If the thing that's red can't be green, or vice versa, if I actually end up saying that something that's logically incoherent, then what might end up happening is I end up producing something that's inconsistent or incoherent or irrational or unreasonable in some sense in virtue of mistakenly assuming that the existentials are always talking about the same thing, or that they're talking about the same thing in this case. So, bottom line, every time you hit an existential, you use a new name. You never use the same name for each existential on a branch that you hit. Why? Because that makes an assumption that we're not entitled to make, namely that it's the same thing that each of those existentials is talking about. All of this, though, is with respect to a particular branch, so we have to keep that in mind, that we're always, when we're thinking about the constraints on how the existential works, that's always with respect to the branch that those things appear on. Okay, so that's the basic idea behind the existential. Here are some quick examples of the existential in action. If I've got EX, PX, I'm going to tick that off and use A, and I'm going to get PA. If I've got QA and then EX, PX, I can tick that off with B and get PB. If I've got QA and PB and I've got EX, PX and QX, I'm going to tick that off with C and get PC and QC. Each time I'm using a new name as I strike that existential on that branch. Okay, so here in the most general form is the tree rule for the existential. So the tree rule for the existential looks like this: EX, alpha, X, alpha, A, X, like that. where I tick this off and I go A for a new name. All right? So this looks a little bit complicated and a little bit horrifying, but it's actually not that bad. All we're saying is, read this as follows. I've got the existential connected to some proposition, and that proposition has some variable x in it that's bound to that existential. And that's really important, is that you're only going to substitute out the variables that are actually bound by the quantifier that you're interested in. So if your alpha has some x variable in it, so if your alpha is the proposition px and qx, like that, and that's the proposition alpha for the purposes of working through this definition, then what we're going to do to get rid of the existential is we're going to strip away the existential, take a new name, substitute it in for x wherever x appears inside alpha. And that's what this here says. It says when you've got alpha, you swap a's for x's wherever x's appear inside alpha. Okay, so the definition as written can be a little bit confusing, but the basic idea is quite simple. If you've got an existential quantifier and you want to deal with it inside a tree, you tick it off, and then for each of the variables that are bound to that quantifier, you replace them with a new name from your sort of list of names that you have available to you inside monadic predicate logic. All right, we come now to the universal quantifier. The universal quantifier is probably the hardest to handle and also induces the greatest degree of complexity with respect to the tree system itself. The universal quantifier, we can get a grip on that by thinking again, as we did with the existential quantifier, about what is true given that the universal quantifier is true. But from there, we're then going to have to look at some particular cases in order to get a feel for what you can actually do with the universal quantifier. And the key thing, sort of a central point of similarity with the existential quantifier and a central point of difference with the existential quantifier. The central point of similarity with the existential quantifier is that you do a similar kind of variable substitution in order to get rid of the quantifier. The central point of difference with the existential quantifier is that you, in some sense, are never finished with using the universal quantifier. So you never tick it off. And we're going to see why it is that you never tick it off in a moment. All right, so let's get a universally quantified statement up. So here's our universally quantified statement. It says, for all things AX. Let's draw a picture of the universe again. And let's suppose that this proposition A is the property of being circular or being round, and we draw our universe, and our universe is in fact full of round things. Okay, so the proposition is true, and remember when we put a proposition inside a truth tree, what we're assuming is that the proposition is true, so we're trying to get a model or a picture of the thing that underwrites that, demonstrates to us what it is for that proposition to be true. So here's the situation where the proposition is true. You've got a universe, it's full of round things. So, what can we do what can we conclude from that when we're thinking about the universe in question? Here's what we can conclude. For anything in the world that we can name, assuming that this proposition is true, for anything in the world that we can name, that thing is round. So, for instance, suppose that I say, well, this thing is A. Well, given that this proposition is true of this world, I know immediately that A is round, and I can conclude that. And suppose that this thing is B. Well, then I know immediately that B is round as well, so I can conclude that AB. Similarly, if I name this thing C, this thing D, this thing E, and this thing F, what can I conclude? Well, I can conclude for each of these objects that I've just named that those things are round. All right? So when these universally quantified statements are true, what they're telling us is that everything inside our domain of objects, everything inside the universe that we're interested in, all of those things satisfy the condition that the universal quantifier is laying down. So in this case, it's saying everything is round, and so anything that we can name whatsoever is going to be a round thing. It's going to satisfy this definition, or satisfy this claim. All right, so given that, how does the universal quantifier actually work inside the tree? Well, let's suppose that we hit a quantifier like this. Here's the rule for the universal quantifier. We can use the universal quantifier, or we can take the universal quantifier, we can substitute in any name whatsoever. And by that I mean any name in the language. You can use any name inside the tree, Or you can use any name that you can think of, and I can put that in, and I can conclude something true, right? So I can put in A, and I can conclude that PA. I can put in B, I can conclude that PB, PC, and so on. So there's a couple of important things to note about what I've just done here. First thing to note is that I didn't tick off that universal quantifier. Why didn't I tick off that universal quantifier? Because I can keep using it for more and more names that I can think of. And there's an infinite number of names inside the language, so in principle, I can sit here using this universal quantifier infinitely for every name that I can think of. So it's in some sense not a rule that you can actually complete or finish adequately, because you'll never be able to write down enough names. There just isn't enough time in the universe to be able to write down all of the names that you'd have to write down, assuming that the universe is finite. Okay, so you never tick it off because it's never done. That's a really important thing. Second thing is that you can run names through it. And to run a name through it, you just grab a name, whichever name, you get rid of the variable that is inside the proposition that's connected to the quantifier, and you substitute that name in for that variable. So here I've substituted in A for X to get PA, B for X to get PB, C for X to get PC, and so on. So that's the second important thing. Third thing is I use this backslash and I write the names next to the quantifier just to keep track of which names I have and haven't used that quantifier for. And that's going to become important later on when we think about how to complete trees inside monadic predicate logic. And so the last thing that's really important to see here is that we've already got a kind of prospect for infinity inside the tree system. Because this universal quantifier and any universal quantifier like it can be used forever, every tree sort of has the potential to go on infinitely if we let it. So we're going to have to try and rein in the tree system a little bit so that it's actually manageable, so it's practically useful and not just useful for gods who have an infinite amount of time to sit there writing down all of the propositions they can think of. Okay, so one more thing about the universal quantifier that's really important to note. So in this example here, I didn't have any names, I didn't have anything else in the tree, it was just the universal quantifier that I was dealing with. But now let's suppose that we've actually got a tree and we've got some names. So we've got PA, PB, and QA, and RC, like that. And we've even got an existential in there as well. Okay? And now finally, we've got a universal quantifier for all x, px. A universal quantifier. And now I want to try and handle the tree. First thing I'm going to do is I'm going to do this conjunction, because that's super easy. I just get QA and RC out, and I just write those down at the bottom of the tree. The next thing I'm going to do is I'm going to do the existential quantifier, because I already know how to deal with that. And I look up the tree, I've got A, B, and C, and I don't have any other names, so that means I've got to use D, and then I write down FD down here, and now I hit this universal quantifier. What do I do with the universal quantifier? Well, one thing I know I can do is I can use any name that I want inside that universal quantifier. Any name that I can think of, including any name that appears inside the tree already. So what I know immediately is that without even having to think of some names, I can run A, B, C, and D through that universal quantifier in order to get, I'll just continue this over here, in order to get PA, PB, PC, PD. Right? And I didn't tick off the universal quantifier because I can keep using it if I want. I could add new names into the tree and then run those through the universal quantifier if I want, but I'm not going to do that. I just wanted to show you that you can use the universal quantifier on any of the names that appear inside the tree for that universal quantifier, including names that have been raised by the existential. So this name, this D, was called by the existential when we ticked that off. And these other names, A, B, and C, were already in the tree, and they're available for use for the universal quantifier as well. Okay, so let's have a look at the rule for the universal quantifier. The rule for the universal quantifier, it goes like this. For all x, alpha, x, A for any name, alpha, A, x. All right, so again, this definition looks sort of complicated and nasty, but if we work through it slowly, it shouldn't be too hard to see the difference between this one and the existential rule. So what we've got to start with is this universal alpha x. And what we're again saying is that we're looking at any variables inside the proposition connected to the universal quantifier that are bound to that quantifier. So we're always, when we're ticking off these universals, we're substituting out the particular variables that are connected to that particular quantifier. And what this rule says is that we can use any name we want and we can then substitute it for every instance of x inside the proposition where that x is bound to that quantifier. And we can use any name we want and we can do it as many times as we want. That's the other key thing about the universal, is that we've got a backslash here. We don't tick it off. It's never completely put to rest. There's always a sense in which you can use it more, although we're going to have a kind of global stop clause governing the tree system so that we don't have to keep using it. Basic idea though is you can keep using it for any name that you can think of, and indeed any name that appears inside the tree. All right, these are the tree rules for monadic predicate logic. So we've only added in 4 rules. 2 of those rules are the straightforward quantifier duals. When you're moving from a negated universal, you switch it into an existential and move the negation over. When you're moving from a negated existential, you switch it to a universal and you move the negation over. Those are fairly straightforward. And then we've got the 2 more complicated rules for the unnegated existential and the unnegated universal. So the unnegated existential rule says that you get rid of your variable and you substitute in a new name for that variable wherever that variable lies, and that name has to be new to the branch that the existential appears on. And then for the universal, you get rid of the universal quantifier, you substitute in any name you want for the variable that appears inside the scope of the universal quantifier. Okay, those are our tree rules. Now, in order to get the proof system to actually work, we have to then rise back up into the sort of meta level, the sort of thinking about the way in which these rules actually work, and we're going to have to modify the completion rule for the tree. And the reason we have to modify the completion rule for the tree is that if we use the old propositional logic completion rule, then we would never finish any tree ever. So remember that old propositional logic completion rule? The old propositional logic completion rule said that a tree is finished either when every branch closes or when every proposition that can have a rule applied to it has had a rule applied to it. Now, remember with the universal, you never tick the universal off. You can always keep using it. So suppose you've got a tree and it doesn't close on every branch. It stays open on a bunch of branches. And on one of those branches, you've got this universal quantifier. That old completion rule is going to tell you to keep using that universal quantifier because that's something that can over and over have a rule applied to it. Which means that that old completion rule from propositional logic is going to tell you to sit there doing the tree for the rest of eternity. No one's got time for that. And so what we're going to do is we're going to try and modify our understanding of completion so we avoid this outcome. Interestingly, the sort of tightest constraint that we can put on the tree system is still going to allow for infinite trees, though infinite trees will be of a particular kind, and I'll talk about those in the next session when we've had a little bit more experience dealing with the tree system. All right. First of all, though, what we're going to do is we're going to modify our completion rule in order to avoid this sort of straightforward case of every tree ending up being infinite whenever it's open. So here's the completion rule that we're working with now. A tree in monadic predicate logic is completed either when every branch is closed, so we keep that old aspect of the completion rule, or when every branch on the tree is saturated. Okay, so we've got this new concept, this concept of saturation, and I'm going to give a definition of that concept now. So a branch is saturated just when every formula on it has had the relevant rule applied. So that's like our old condition from the propositional logic tree system, namely that everything that can have a rule applied to it has had a rule applied to it. So we sort of keep that clause, but now we add in a unique clause for the universal quantifier. Every formula on it whose main operator is a universal quantifier, 1, has had the universal quantifier applied to it at least once, and 2, has had the rule applied to it once for each name that appears on that branch. Okay? So the easiest way to see how saturation works is to look at a particular example. So here's suppose I've got this basic tree, PA, there is something QX, and Rx, and then for all x, if Px, then Qx. Okay, so there's my tree. Now, what I'm going to do is I'm going to work through the existential quantifier and then work through the universal quantifier, and I'm going to try and complete the tree. So first thing is that I have to use the rule that I have to apply a rule to everything that can have a rule applied to it. So I have to apply something to the existential quantifier. I also have to use the universal quantifier at least once. Right? That's part of the condition inside for saturation. And the second thing I have to do in order to fully saturate the tree is use the universal quantifier for every name that appears on the branch that quantifier appears on. All right, so first thing I do is I introduce a new name for my existential quantifier. I had A up here, so I've got to use the first unused name, and that's B. And then I get QB and RB like that, which gets me, once I deal with the conjunction, QB, RB. Now, I've got to use the universal quantifier. I have to use it at least once, and I have to use it for every name that appears in the branch that tree is on, and that's looking down and up the branch. So the universal quantifier looks up the branch and sees an A, so we know we're going to have to use the A on the universal quantifier, and it looks down the branch and it sees a B, so we know we're going to also have to use the B on the universal quantifier in order to get to the point of saturation. So let's start. We put an A through first, and we get P, A, arrow, QA. And now what I'm going to do is I'm going to use the conditional rule on that to get not PA, QA. And if I look at the tree, I've got this not PA here and this PA here, and any proposition and its negation like that, where you've got the basic proposition and its negation, that's going to close. I'll talk a little bit more about closure in a moment, but basic idea though is that closure here is the same as closure as it was in the propositional logic. It's just that what constitutes a basic proposition has changed. A basic proposition is a proposition followed by a name, like a predicate letter followed by a name, and then the negation of that predicate letter followed by a name, followed by the same name. Okay, so I've used the A for the universal quantifier. Now I'm going to use the B, and by using the B, I've saturated the universal quantifier, because what I've done is I've used it once, I used it at least once, I used it once when I used it for A, but now I've used it for every name that appears on the branch that universal quantifier appears on. So what I get down here is PB arrow QB, and then I break that conditional to get not PB on one side, QB on the other side. All right, and now at this point, that completion rule tells me that the tree is finished. It tells me that the tree is finished because it's not the case that every branch closed, so we don't trigger the sort of closure rule of the completion, the closure dimension of the completion rule. So at least one branch is open, and now we have to work out whether the tree is finished without closing all the branches. And what does it take to finish a tree in monadic predicate logic without closing all the branches? Well, the other way is to saturate the branch. And to saturate the branch, we have to have used every rule that can be used in that branch, and we have to have used the quantifier for every name that appears on that branch, and we have to have used it at least once. So if we look here, we've done everything that's not a universal quantifier rule, so we know we've used all of the rules that we can use in order to get to that point of saturation, and then we've used the universal quantifier for the two names that appear in the tree, the A and the B, or appear on that branch in the tree. And so now we know that we've saturated the tree because we've used the universal quantifier for every name that appears on that branch. Now, importantly, saturation is something that applies to particular branches. So saturation is a sort of global feature of trees. You have to use the universal, you have to saturate the entire tree in order to complete the tree. But what saturation really is in the sort of focusing on is the way that the universal sits on a particular branch. So if I had another branch, so suppose this is one branch of the tree, and then I had another branch down this side, and I had sort of P, A, and then I had for all X, QX, like that. Now I've got to work out how to finish the tree. Well, I have to use this universal at least once, because in order to finish a tree, I have to use every universal inside the tree at least once. And now but I also have to then saturate that universal, which means I have to use it for every name that appears on the same branch as that universal. So I look at that branch over there, and I see that there's one name appearing on that branch, namely lowercase a. And so what I do is I put A through that universal in order to get QA. Now here's what I don't do. I don't read up that branch and then down this branch and then use the information over here to saturate that side, which is to say I don't have to take the B that's on this right-hand branch and then run it through the QX on that left-hand branch in order to saturate that left-hand branch. Saturation requires that you saturate every universal with respect to the branch that it appears on, not with respect to the entire tree. So we only have to run A through this universal in order to finish this side of the tree, and we have to run A and B through this universal in order to finish this side of the tree. Okay, so that gives us a new completion rule, and now the last thing we need is to just focus on our closure rule, and then I'm going to introduce something called the order of operations, which tells you the order in which you have to do rules inside the tree, which we didn't have in the propositional logic case, so that's going to be new here. So the closure rule, inside monadic predicate logic, you close on things like this. Okay, so here I've got PA and not PA, and I've closed. So here are the things that you have to have in order to close a particular branch. You have to have the predicate letters be the same, so you have to have the same predicate letter in the basic proposition and inside its negation. And the names have to be the same as well, so you have to have the same name inside that. So here are two things that, so this is correct. Hang on, do it in green so you can see it. PA, not PA, closed. So that's good, that's correct. Now here are two things that are incorrect. First thing is you've got PA and then you've got not QA and you close on that. And the reason that this is bad is because the predicate letters disagree. They're not the same predicate letter. It always has to be the same predicate letter in order to get closure, or at least to sort of close a particular branch. The other thing that's not allowed is if suppose you've got PB like this, and you get not PA, and then you close on that, right? So it's not just the predicate letters that have to agree, but the names also have to agree in order for you to close that particular branch, right? So what you're looking for when you're looking for closure is a predicate letter and the negation of that predicate letter with exactly the same name falling inside the slot following the predicate letter in order to get closure. That's what you close on. You don't close on either of these other things. And that has to happen on a particular branch. So if you have branching like this, and you have PA over here, and you have not PA over here, and then you close both branches because you've got a proposition and its negation inside the tree, then you've made a mistake. The proposition and its negation have to appear on exactly the same branch, and here they're appearing on different branches. So what is okay is when you have a branch like this, on one side you have PA and not PA, and you close over here, and over here you have QA, not QA, and then you close that. That's going to be an acceptable way to close those two branches. This sort of thing is not allowed. Okay? Very last thing, and then we can finish off, and in the next session I'll go through some worked examples so you get a sense of how to do this, is the next thing is we've got an order of operations. So in the propositional logic case, you could do any rule in any order that you wanted, so long as you did them all and you got to the end of the tree, you were fine. In the monadic predicate case, we actually have an order of operations that we use. Now, the order of operations that I impose is in some sense an order of operations that is specific to this particular course, in the sense that you don't actually have to have this order of operations in order to get the right result outside of this course. So if you're working with logic inside computer science or just inside arguments more generally, you don't have to use this order of operations. But in order to be able to produce the results that I want from you in this course, you have to use this order of operations when you do your trees. So for your purposes, you can consider this as absolutely ironclad, that you have to do your predicate logic and general predicate logic trees, as we'll see when we get to them, in this order. So, first thing you do is you do your propositional logic rules. So the propositional logic rules are your rules for and the arrow, and the or, and the biconditional, and their negations, right? So you do all of those first. Do that in black so you can see it. Then you do negated quantifier rules. So you do your not EX or your not universal X, okay? And then you do your unnegated existential rules, and then you do your unnegated universal rules, and what you do is you return to the top and cycle through. Now this cycling is a particular kind of cycling. It's always trying to, but basically this is sort of an order of priorities. You have to do certain things as they arise before other things. So for instance, suppose you do a bunch of things and you end up with some propositional logic rules that you didn't have before, then you have to do those before you do anything else. If you do a bunch of things and you end up with some unnegated existential rules, then you have to do those, and as long as there's nothing else that takes priority, you have to do those before anything else, and so on for each of these rules. So it's not like you sort of do all the propositional logic rules and then you're done with propositional logic rules for the tree. This is more an order of priorities. You start with the tree by doing the propositional logic rules that you can. Then you look at the tree at the next step. So at each step, you sort of run this ordering. At the next step, you say, okay, are there any propositional logic rules to do? No. Okay, then I move on to negated quantifier rules and you do those. And then you look at that next step. Are there any propositional logic rules to do? No. Are there any negated quantifier rules to do? No. Are there any unnegated existential rules? Aha, yes, there are some, so you do those, and so on. So you sort of keep applying this list of priorities at every stage in the tree. Okay, we'll see how that works in the next session, where what I do is actually take some of these trees and I'll work through some examples. And then following on from that, we'll also talk about doing counter models and working out how to test particular arguments. And we'll also have a look at some infinite trees. All right, until next time, get some practice doing some of these trees if you can, and have a look at those rules and make sure that you got a pretty solid understanding in particular of how the universal and the existential rules work. Okay, thank you.